This is part 7 in a series of videos in which I am restoring an ASR33 Teletype machine. So far in these videos I've gone over the basic chassis, dismantled it, restored the printer, the keyboard, and in the last video I looked at the punch. And in this video I've decided to look at this, and this is the electronics pack out of the machine. So this is where all the wires and cables come together. So we have the interface to the outside world, which is just really the current loop connections and the power connections. The power supply for generating the current loops, driving the various components. We've got a driver board here, which is the driver board for the selector magnet, a big electromagnet that drives the system. And then we have various other cards for controlling power to various parts of the system, as well as generating the current loops. Supports two different current loops, 20 milliamps and 60 milliamps, and there's a whole range of options that you can use with this, including the tape reader and punch, that sort of thing. But these also would support a rudimentary modem as well, so a whole range of things and options that they have, hence all the connectors. A lot of these aren't used on this particular machine. As you can see, this machine has a huge bundle of wires hanging out the back, and I'll be removing these. It's actually got a separate current loop connection on here as well, so I'm going to get rid of that, and I intend to use this on a current loop to RS232 in full duplex mode, so that's how I will be wiring it up. I'm not quite sure how it's configured at the moment. We'll have a look at that. But what I'm going to do to start with is get these wires out of the way. So we have one auxiliary current loop here. We've got the main input-output current loop, and then we've got power. It's actually a 120 volt machine, or 117 volts if you look at the manual. And in this particular machine there's a big dropper transformer in the bottom of the stand. It drops 240 volts to 117 volts, and that's what this wire is normally connected to. But I'll get it out of the way for now, just so that it's easier to work on the machine. I'll get rid of the rest. I may replace or shorten some of these wires, and I'll get rid of this one altogether. So I'll get these out of the way, and then we'll start looking at the rest of this unit. Okay, well that's the wires out of the way, and gives me far better access, so I can see what I'm doing, and I don't have a huge bundle of wires to work around. So the next thing I'm going to do is pop out the amplifier, the driver board, and we'll start looking at some of the components. The only components really I suspect that may give us some problems are the capacitors. This one especially is looking a bit the worse for wear, and what I'll do is just pop the boards out and then give this a really good clean as usual, so we can see what's going on. And I'll then go through, measure everything, and if I find any faults I'll rectify those, get it refitted, and we can start trying to power up the unit. But we'll get this out of the way first. Be very careful here, because these are very easy to snap off. So you can see this board generates quite a bit of heat, and I will need to clean that off, but nothing looks too bad on there. I will of course measure all the resistors, make sure they're all within spec. I'll do that separately. I can now do the same thing and remove this board here. So this is again very easy to remove. It's on a couple of plugs here, so I can just pop those off, and then I can slide the whole board out. So I'll get this out of the way. Okay, so that's that out of the way. So I can now gain access to all the parts I need to. What I'm going to do now is take this away, give it a good clean, and we can then start looking at all the various parts and see what sort of condition they're in. Capacitors do look a bit worse for wear. Looks like the vents may have started to open. showing cracking around the vent, so these capacitors may need replacing. Can't really see in that one, but again, I've got a good capacitor tester that'll let me test them up to their full working voltage, so I'll put them on that to make sure they are all usable, and if not, I'll have to try and source some replacements. I can't see any signs of anything having been burnt or any wires charred. Just have a quick look at the fuses. Okay, well the fuses all look to be intact, so that's quite a promising sign. There is one more fuse on this board. Which also looks to be intact. Okay, so I'm going to get this cleaned and see if we can figure out if it needs any parts replacing. Okay, I've been through this with the multimeter, given it a good clean, as you can see. I disconnected one terminal from each of the main capacitors and ran a proper leakage test on those and capacity test, and they seem to be fine. Same with the capacitor on this board, and I've checked as many of the other components as I can. All the resistors seem fine. They're all reading as they should. There's no damage I can see to the board. All the black soot, or at least most of the black soot, just cleaned off. You can see there's still a bit of discolouring of the board, but all the black sooty deposit is gone. And the rest of it I've checked through as much as I can, and it all seems fine. The windings in the transformer read okay, but I won't know if they've got any internal shorts until I try applying power. And all the rest of it has cleaned up very nicely. What we have here is, this is the main terminal strip that connects the machine to the outside world, and we have basically the transmit receive current loops coming here, along with the mains power and some control signals. So what I can do now is get this reassembled. I'll refit the boards I've taken out, and we can then try powering it up. I'll try manually testing the solenoid drive circuit before we put this back in the machine. I'll reattach the mains cable. I'm going to leave the current loop off for now. I want to control that manually, at least to start with, until I'm fairly certain that the rest of this is working fine. We can test the supplies, rectifiers, make sure all this works the way it's meant to. We can check the mode switch. So we can test a lot of this functionality wise before we really start trying to use it in the machine itself. Again, I've tested all the power resistors. They'll read exactly what they're supposed to, or at least within tolerance, and everything else seems to be exactly what it should be. So as I say, I'll get this reassembled, and we'll try putting some power into it. Okay, so that's reassembled. All went back together quite nicely. Nothing's broken. All the fixtures and fittings seem to be present. I've left the protective caps off the capacitors. What I'm going to do before we refit this to the machine is run through some basic tests on it. Just make sure that the various supplies are correct. I prefer to do it this way around rather than just fitting it to the machine. Make sure that the various parts are at least fundamentally working and that we don't have any major issues. On all equipment like this, what I really don't want to do is damage other parts of the machine. This hasn't been run properly for decades, so I want to make sure that we give it the best chance we can of powering up without any damage. So to achieve that, what I've done is I've got it temporarily reconnected to its mains lead, but I'm powering this through a dim bulb tester. If you're not familiar with these, it's nothing more than an incandescent bulb in series with the supply. And what will happen here is if there is an issue with the unit and it draws excess current, what will happen is the bulb will light up, its resistance will increase, and it will limit the current that the unit can draw, and that will protect the unit. And depending on what you're working on, you just put a different wattage bulb in. The higher the wattage, the more current it will supply. And to give you an idea of how useful that can be, what I'm going to do is simulate a dead short on the main supply coming into this. I do not suggest you do this unless you're absolutely certain you know what you're doing. I'm just doing this for demonstration purposes to show the function of the dim bulb tester. Okay, so I've got a test lead, and what I'm going to do is I'm going to clip this directly across the incoming mains lead. So this is going directly from the live to the neutral, and obviously that's definitely not something you should do unless you have a dim bulb tester or something similar, some sort of current limiting. Otherwise you are going to blow something up. So just do not do this unless you're certain you understand what it is you've got connected. What I can do now, even though there's a dead short now effectively within this, I'm simulating a dead short within this unit. If I turn the power on and start to increase the mains voltage, what you'll see is the bulb starts to illuminate, and it's limiting the current. It's just going to go up to full brightness without any damage occurring. If we did the same thing without the dim bulb tester there, then even at sort of 60 volts, the main supply would be able to put a huge amount of energy into the component that's created the short, and of course it would do a lot of damage. So this is a good way to protect this unit from further damage if there are any faults within it. Okay, so we'll get rid of the short, and the first thing I want to do before we start any testing and really applying any power to it is just check for any leakage to ground. We get a little bit, but it should be in the order of mega ohms. If it's just a few K, then we have an issue. And just make sure the ground is actually connected, which it is. So that's extremely good. I'll just try it the other way around just to be certain. Okay, so that's extremely good. We're getting over 20 mega ohms, which is absolutely fine. The next thing I'm going to do is start applying some power to this. I'm going to initially run it at fairly low voltage, so I'll run it at maybe 60 volts. It is a 120 volt unit, so I'll run it at 60 volts. That should give us approximately half the expected voltage on most of the supplies. So we should have, this is a 20 volt supply across this cap, so we should have around 10 or so volts across that one, and then the one down here is a higher voltage, so we'll probably get something around the sort of 20-30 volts across that one. This board here is the reader supply board, so it supplies power to the tape reader, and again I'll test the voltage coming out of this later. There's not a lot on this board, it's just really a capacitor and a few resistors, so I've already tested those, so I don't really expect any faults with that. But I want to properly test the solenoid driver amplifier to make sure this works. This is where you tend to get most problems on this. So the way this system works is it generates one or more current loops, and in half duplex mode, and the mode it's in depends on how it's wired up. In half duplex mode there's a single current loop, and each end, this machine and the one it's talking to, work on a common loop. Only one unit can send data at any one time, of course, and the way they signal is that they just open and close the loop. So when the loop's closed by one machine, assuming the other machine also has the loop closed, you'll get 20 milliamps or 60 milliamps. This supports 20 and 60 milliamp loops. You'll get current flowing through the loop. When either machine opens the loop, obviously the current will drop to zero, and this board is responsible for providing that current. One of the machines in the loop somewhere has to provide the current for the loop, and again that's dependent on how you wire the machine up as to which machine is doing that, but also this board detects the current and through the power transistor it turns the selector solenoid on or off in response to the current that's flowing. This is wired up at the moment in a way that it will give 20 milliamps through the loop, but because most of the circuits are not connected to anything, we can't just use the normal receive and transmit current loop connections because there's nothing effectively configured, because we don't have these plugged in, so they're not going anywhere. But we can still simulate that fairly easily. But before we get onto that, we'll just briefly test the supplies. Again, what we don't want here is for the bulb to light up. So I'll slowly increase the voltage, and running it at low voltage obviously gives the capacitors a chance to recover if they've been sitting idle for a long time. We're drawing 50 milliamps from the mains, and I will try measuring the voltage on the supplies. Put the meter where you can see it so I'm not getting in the way. Hopefully you can see it there. So this one we should be getting probably 10-11 volts. Which we are. Got the probes the wrong way around there. Okay, and this one will be somewhat higher voltage. I try to keep my hands out of the way. Okay, so that's looking quite promising. I'll leave at this voltage for now, and we'll test the driver amplifier. As I said, we can't just close the circuit on the normal interface connector because there's nothing going to it at the moment, or at least not all the way. There isn't a complete loop. But what we can do is simulate a loop, and so we'll do that now. And so that we can see what's going on, I'll put an LED across the actual solenoid connections. Otherwise we won't be able to see if it's actually doing anything. So I'll just turn this off. Okay, so I don't know if you'll be able to see that or not, but there's now this LED is across where the solenoid would normally be connected to. I'll put the meter into current mode. And if I now simulate a closed current loop, then the LED should come on. So hopefully you're going to be able to see the LED. Let's turn this around a bit. Okay, so you can see it's glowing dimly. That's just leakage in the transistor, but this is a 500 milliamp constant current driver, so normally it will have a kind of high load across it in the form of these solenoids. So the glow you're seeing from the LED when there's no loop closed is just leakage in the driver transistor, which is not an issue, but it should go very bright when we close the loop. So all I'm doing here is going from the source of the current in the current loop to the point where the loop will be closed. So if I do this again, you can see it on the meter. We're drawing about 8 or 9 milliamps, which is about what we'd expect. Just raise the voltage a bit, so we're around half of the normal voltage, and then we should be drawing about 10 milliamps. Try that again, and as you can see, we're up around the sort of 9 milliamp point, which is correct. Half of the 20 milliamp we would normally get. That's not drawn by this LED, so that's not the LED drawing 20 milliamps. This is effectively the current loop going through the meter, and the LED showing the output from the solenoid driver. So that's looking quite promising. Just to clarify what's going on there, we'll look at the schematic. So this is the schematic for this board, and what we've got here are a couple of resistors fed from a regulated supply, and the value of the two resistors is such that if we take one of the resistors to this point, which is the other end, if you like, of that supply, so it's effectively ground, then we'll get 20 milliamps flowing through the resistor and to ground. if we use the other resistor, we'll get 60 milliamps. And the way this would normally work is, depending on how you wire the connector at the back, you connect one wire on that connector to one of these 2 points. If you want a 20 milliamp loop, you connect it to this one. If you want 60 milliamps, you connect it to this one. And that is if you want this machine to provide the current source. It might be that the machine on the other end of the loop is providing the current, in which case you can leave this open. But assuming this is providing current, then what will happen is these 2 wires go through the connector on the rear. They go through to the machine at the other end of the connection. It will then open or close this loop, and that is detected by this circuit, which in turn drives the solenoid. The reason we need to kind of short it across these 2 points is because this connector that normally plugs in here is not present, and so I'm having to effectively short from this connector across to this point here. So I'm effectively closing this loop by bridging from here up to one of these 2 points. But as you can see, the entire circuit's working. The LED is across this point, so although we're shorting down here, we're just proving that this entire circuit's working the way that it should do. Okay, I'll go through the rest of the circuit. I'm just going to do exactly the same thing, just check that all the supplies are correct, that I'm getting the right connections going to the various inputs and outputs, and then this will be ready to go back into the machine. Before I do that, I'm going to actually turn the voltage right up to 120 volts. I'm going to leave it for 6 hours and then come back and have a look at it and make sure that it's still behaving itself. But at the moment it's looking quite promising. There's no odd smells or smoke. It's just whether or not the capacitors are going to survive and whether or not any of the transformers has any internal issues. Okay, it's been going now for a little over 5 hours, so I'm going to call that a day and get this put back into the main chassis. As you can see, the bulb is still off, so nothing has gone short. I've just rechecked the supply voltages and they are fine. It's now running at 120 volts. So it looks like the electronics pack is working the way it's supposed to. Before I put this back in, I'll get the mains wire properly reconnected and the wires routed the way they should be. It's just kind of hooked up loosely at the moment. And then we'll get the chassis onto the bench and get this refitted. Okay, I've got the chassis ready to accept the electronics pack. I just need to refit the protective caps on the capacitors. Make sure all the cables are routed out of the way. I have refitted the insulation and secured the keyboard cable down, and that's all now sitting in the correct place, so I can drop the electronics pack into the chassis, and again I'll refit the cover onto the distributor and the guard plate. So I'll do that next, and then I'll get this power pack put in and we'll have a look at it and see how it looks once it's been refitted. Okay, that's the electronics pack refitted into the machine. I may need to adjust the front end of it slightly so that the shaft on the selector knob properly lines up with the cover. I've got it set, I think, where it was, but we'll check that once we've got the front cover refitted. I haven't plugged in the connectors yet. The next step before I can really power this up is I've got a bit of work to do on the printer. Specifically, I need to replace the rubber bumper that's on the print head. If I try and run it with that bumper in its current condition, it will destroy the print head, and they are extremely rare and hard to get hold of, so I don't want to do that. So in the next video, what I'll be doing is finding a way to replace that rubber bumper. There are various different methods you can use, so I'll show you how I normally go about that. And then once we've got that done, we can actually start trying to power the machine up and see what it does. So that's for the next video. Any comments welcome. If you have one of these, I'd be interested to hear what you use it for.